I want to show you now how to enter these a matrix, a system of linear equations in Octave. It's pretty simple if you write the system in the matrix format. Now here is the example again with 4 variables and 4 equations. There are 2 ways you can write the system in the matrix form. There is the matrix algebra format, which you probably saw in a video before, or you probably know this before. You can write this system here into a matrix equation. So this first matrix here, it's called the coefficient matrix. This little matrix here, column matrix, that's the big X, that's the matrix of the unknowns, okay? And then the right hand side of the system can also be put in a matrix, in a column matrix. So this way your matrix here will look like a matrix equation. So you can actually write that as A times X equals to B, and then solve for X. X here is the big X, okay? It's a vector. So you can do that way, or you can simply write the augmented matrix and put that into the whole thing into a matrix. So here, this would be augmented. Now, this matrix A here is not the same one as this, same matrix as this one. You can clearly see, right? This matrix has 4 columns and 4 rows. This matrix has 5 columns and 4 rows. Now, it depends on the situation. Eventually, we're going to use this format. We can write a program to do Gaussian elimination for us. And then we can enter the coefficient matrix and then the right-hand side matrix. You can do augmented matrix, which is the same process, but it's just a matter of taste, really. Okay, so let's enter a matrix in Octave. Here's an example just to get it started. So here's a system of 4 equations and 4 variables. And I don't know the solution of this system, but we'll find out. So how do we enter that in Octave? So let me pull Octave here and then type that matrix. Okay, let me push this matrix here, or this system, over to this side there. Okay, now I think we can see Octave here. Alright, so I'm going to use the matrix equation format. Here is how we enter the matrix. The matrix A will have the entries 3, -1, -1, and 2. So that's the first row. 3, -1, -1, and 2. You can simply use a single space to separate the entries. Octave will know that if you put a space, then it's a new entry. So that's the first row. Let me enter the second row, which is a 2, 1, -1, and 1. 2, 1, -1, and 1. Semicolon. So that's the second row. The semicolon separates the rows. Third row is 1, 1, 0, and 3. Okay, 1, 1. There's no x3 in there, so it's 0. The coefficient is 0. Finally, -1, 2, 3, -1. Close bracket. That's a matrix A. Now let me enter the matrix B. B is, now B has to be a column matrix, so it has 4 rows. Okay, so I put the first row, -3, semicolon, second row is 1, semicolon, 4, semicolon, 4. All right. Now Octave has a built-in procedure to solve systems very easily. You can simply do x equals, this x here is actually the column matrix, okay? So it's a column matrix because you will use, you can do a inverse, so a raised to negative 1, and then times, well, times like that, b. Okay, so we're solving this system by doing x equals to a inverse times b. So it turns out that the column x is, okay, and here's a solution, 1, 2. This number here is so small that I'm almost sure that the solution is 0, okay, because it's 5.6 times 10 to the negative 17. You know that's the reason that Octave writes like that. It's probably of the rounding errors, right? The procedure that Octave uses, it might be Gaussian elimination that Octave uses. So the round off errors will give you a number that is very close to 0, but it's not actually 0 there, as you can see. But I'm pretty sure this is 0. We can test that. We can test. Let me write a new vector here. Let me create vector c, for example. C would be negative 1, semicolon 2, semicolon 0, semicolon 1. Let's see. So if I multiply, right, if I multiply this guy here, if I multiply a times x, I should get b, right? Because it satisfies the equation. So if I multiply the matrix A times this vector here, this matrix, I should get the right-hand side, which is negative 3, 1, 4, 4. Let's test that. Okay. So multiply A times C, there it is. That's the right-hand side, right? Negative 3, 1, 4, 4. So it is a solution. So I want to show you how to do Gaussian elimination by hand, well, not by hand, but using Octave, doing those row operations that we saw before. So this time, I'm going to write the system in an augmented matrix format. Okay, so this would be easier for us to understand how Gaussian elimination works. So let me write matrix A again, but I will write in an augmented format. So B3, negative 1, negative 1, 2, negative 3. Okay, so I'm adding now the fifth column there. Now it's an augmented matrix. 2, 1, negative 1, 1, 1, 1, 1, 0, 3, 4, negative 1, 2, 3, negative 1, 4. Okay, it's an augmented matrix. Now let's apply those operations that we saw before. So just to refresh your minds here. See, remember this? The first operation. Okay, let's do Gaussian elimination here on that matrix. So this is pretty cool. What you can do here is to multiply. So it takes the first, if you look at the operation there, I should move this over. Yeah, there we go. So I want to simulate that operation there. Take the first row of the matrix. In Octave, to refer to the first row of the matrix, you simply do A parenthesis, and then you do 1, first row, and you don't put columns, you just put column there. See, the column means that you're not specifying any column. Octave will take all the columns from that row. Okay, you're just specifying the row, but you're not specifying any columns. So if you do that, Octave will return or will give you the row. That's the first row of the matrix. Okay, let me put the matrix here. Here's the first row of the matrix if you want to see it. If you want to see, let's say, the third row of the matrix, there. If you want to see an entry of the matrix, like let's see A22, what is A22? And then you put A22. See, it gives you 1. That's the coefficient of the second row and second column. As you can see here, second row, second column, right? If you want to get one column, then you do A parenthesis column, and then see if you want the third column. That's it. See, that's the third column of the matrix. Okay, so we're going to do operations. So here it is. Take the first row. Okay, so I'm just translating this operation to Octave. So it takes the first row multiplied by the opposite of A21 divided by A11, and then add the second row. See, that's the second row. That's the operation that gives you. But we have to put it in row 2. So what we can do here, so I do row 2 equals that. Okay, so it's pretty simple. Look at this. I'm just translating this into Octave. So whatever this operation is, I need to put that in row 2. So I simply do, okay, row 2, here's row 2, would be equal to that. Okay, row 1 times opposite of A21 divided by A11 plus row 2. Look at what the new matrix A look like now, right? 0 here, right? So that coefficient or that term is eliminated. So let's do the second operation here. So we put that in row 3. So it's row 1 times the reciprocal or the opposite of A31. See, I'm copying right here. Row 1 times negative A31 divided by A11, close parenthesis, plus row 3. There it is. Look what happened. Right? Eliminated that term. And then the third operation would be row 4. 1, this would be 4 here. Add that to row 4. There it is. Oops. Yeah. And then let's do the other operations. Now this is, we're going to replace row 3, okay? Will be equals to row 2 times negative A32 divided by A22, and then plus A33. because it's row 3. See here? There you go. So you eliminated that term. Now let's eliminate this one. That will be this operation here. 4, a 2, and this would be 4, 2, add to row 4. Alright. Yeah, Octave is pretty funny here. It put -0. That's because there's a round off error in there. This is actually very close to 0. If we do format long, you will see that it's, I think you will see what that is. Oops, I don't want to do the operation again. Yeah, it still uses -0. That's because it's 0.00000, and then eventually will be a 1 or some number. It's not quite 0, but it's pretty close to 0. Let me go back to format short. Okay, well, anyway, this is 0, 0. Now let's put a 0 right here. That's the very last operation here. That's this one. A4 equals to A3 and times negative A4, comma 3, A33 plus A4. There we go. Okay, so that's the final operation. Look at the matrix now. The system, you can see the system now. It's a triangular system, right? Look at the last equation. The last row, which represents the last equation, it's -13 x4, right, equals to 13. You can tell that x4 is 1, right? Because this is what we have now. Okay, let me copy that here. Okay. So we are doing this is after Gaussian elimination. See, you can tell here that this is -13 x4 equals to -13, and then 0.6 x3, right, plus 2.6 x4 equals to 2.6, and so forth. Right, you can tell that x4 is -13 over -13, which is 1. Then you can get x3 here. I won't do that, but it just to show you that it can easily be done. So that's the idea. Next time we're gonna implement that in a program.